who remembers this gentleman? Young Jim. I think this is the first time that young Jim hasn't been here when I've been speaking for quite a while. He sends pictures and a message. He grows strawberries and he grows beans. There are the strawberries, there are the beans, and there he is, smiling slyly at us at the control room. You box him, and even better, he sends us a message. Now, he didn't know I was talking to you, so he sent it the wrong way. But if you just make the substitution halfway through, all will be well.
Good to meet you in the old 2BH here. Just dropping into the call rooms at Whangarei to say, hey, sorry I can't be with you tonight, but Gary's here. He'll sort you out. But seriously, you have a great 2012, everyone. I've really enjoyed your hospitality over the years, and who knows, I may be able to drop back sometime. In the meantime, don't forget, NZART Conference is down here in sunny Nelson. Promise you a good time. Maybe we'll see you. Have a great night and a great 2012. Bye-bye.
That concludes our commercial break from All right, what am I going to talk about tonight? What triggered this talk is that nearly a year ago now, I was hiding out the window on my deck and I sat down on a stool that wasn't there and I fell backwards off the deck, 5 feet to the lawn, and as I rotated through the air thinking about a break fall, my right side came in contact with the hose reel and I broke 2 ribs, depending on which doctors look at it, between 2 and 6 ribs. And this was quite painful, so I went to the emergency services that night and this is what they showed me. My right lung had collapsed, only half of it was working. In fact, it didn't seem to be taking in any air at all, and it had this complicated name here. This is not good. So anyway, they sent me home with some painkillers, and it got worse and worse and worse. So I went back a week later, when I could hardly breathe at all and hardly walk, and it got worse. Even more of my lung had collapsed. So they gave me a transfusion, called an ambulance, whipped me into hospital, and in hospital they put a tube into my pleural cavity. The little hole is still in there, a half-inch hole made of plastic, and I was in hospital dragging a little cart around for 4 or 5 days, which filled up with 3 litres of bloody effluent, because ribs had been sticking out into the pleural cavity and abrading it and bleeding into it. So this did not seem to be good. You could see a bit of the gunk that was in there. However, it all came right eventually, and a year later, my lung looks like this. This is the heart incidentally over here. It's not a funny tumour. And you can see it's not quite as big as the other one, but I'm alive and it seems to have come right. And I have to say now, do we have any doctors in the house? We don't, do we? We have a wonderful medical service in New Zealand. This didn't cost me a bean. Think about what that would have cost if I was living in the US of A. So this set me thinking, and I thought, I have experienced X-rays, many CT scans. I have experienced ultrasound scans, and I talked to the people who administer these. Such interesting physics. I thought, I will talk to Branch 29 this year about the physics of medical imaging. So, here we go. How they look inside the body. These images, of course, are made using X-rays. Now, this is a bit small, I'm sorry, but don't worry, it gets bigger. The radio waves that we emit are down here. This is a spectrum going from 10 to the 16 meter. Oh, there's 50 meg. This runs from 50 megahertz to 1,000 megahertz. So the radio spectrum is down here. If we go up a little bit further, we get into the visible spectrum, which is very narrow. And it runs from about 700 nanometers up to 400 nanometers, or the other way. That's the wavelength. So a nanometer is 10 to the minus 9 of a meter. Very small. But they're still radio waves. If we go a bit further to between 10 nanometers and 0.1 nanometers, that's in the region of 10 to the minus 9, 10 to the minus 10 of a meter, then we get into the region of X-rays, which have got quite different properties. So it's all electromagnetic radiation. These rays were discovered in 1995 by this joker, Wilhelm Röntgen. Did I get that right, Henry?
Near enough.
Good. And people thought this was quite clever, so they gave him the Nobel Prize in 1901. He discovered them by accident. He had this thing here, which was called a Crookes tube. Some of you may have seen these at school. Back in the good old days, where you have an evacuated glass bowl. Actually, it's not quite evacuated. It doesn't work if you've got complete evacuation. And you have a cathode at one end and an anode at the other end, and you put a high voltage between those two and turn it on. And what you see is a beautiful image in blue on this bit. It's a bit like a cathode ray tube, old-time cathode ray tube, caused by some sort of radiation coming through and striking the glass here and fluorescing in the glass. And it was fairly rapidly discovered that these were electrons, which are stripped off the atoms in the very nearly evacuated air inside. But Roentgen also found that he had a fluorescent screen a little distance away from this, and in the dark, where he was looking at it, he could see this screen fluorescing slightly. And he wondered what this was, and he determined that some unknown radiation was coming out. We now call them X-rays. He called them X-rays because in algebra, X is the unknown, and he didn't know what caused them. And he found that they weren't deflected by magnetic fields, and they penetrated many kinds of matter. So there we are. They also penetrated flesh, which was very interesting, but they were stopped by bone and lead and metal, and they darkened carbon photographic plates, which of course is the way we take X-ray now. This is very interesting. Just let me digress and go back to the origin of photography for a minute. In 1826, Niels Bohr, who was a Frenchman, a very rich one, he lived in the chateau, was interested in chemistry, and by mistake he left a jar of silver nitrate solution on his window ledge one day, and he noticed when he came back in the evening it darkened. And eventually he succeeded in taking the very first photograph. You could see this on the web, actually, which is a picture taken from the wall, from the window of his chateau. It was an 8-hour exposure on pewter coated with bitumen of Judea. I don't know what that is. Developed by washing with lavender and white petroleum. We use rather more mundane products these days. So this is 1826, but by 1895, wet plates had been developed for a while, and Roentgen could use them to make his X-ray images. And in fact, this is the first X-ray ever taken, and it was taken by Roentgen in 1895. What he did, he got somebody to put a hand up against a photographic plate, and he let the tube run for a while, and this is what he got. This is down in the museum, hence the badge down there. He looked at it and decided it was fuzzy. The problem was the rays were not collimated, and so he put the rays through a very small pinhole, and he got a much better picture here very shortly afterwards. And it shows a ring on a finger here, and these are the bones, and you can see the shadowy outline here. 3 weeks later, a secondary school teacher, Heinrich Hoffmanns, did this X-ray here in his school laboratory with one of these simple lamps of a 21-year-old female hand. It says female hand. I assume the female was also attached to it at the time. But anyway, 21 years old, and this exposure took 90 minutes. That's a long time. And this, like all of the other ones I'm going to show you, in the early days, X-rays took a long, long time and could be very dangerous. Here's the first medical X-ray being taken in the US by the doctors Frost. And they used a Poulouge lamp, which is a type of gas discharge tube. Here are the two doctors sitting here, and here's the patient with his hand over a photographic plate. There's the bright, shining lamp here, and there's the patient's wife sitting along there looking very nervous. The medical professionals, they often are, were very quick to jump on this and thought, aha, here's something we can use. But they didn't understand the dangers. Nobody understood the dangers, let alone what these rays were. And so they used extremely high doses. And this is a picture of a hand of a doctor who had been routinely doing X-rays for 50 years. His hand was just completely eaten away by tumours, you see. But nobody knew what these rays were. So the first clue was given by this gentleman, Johann Balmer. Balmer series. Did you study the Balmer series at school? Does that ring a bell to anybody? No?
You get conversions. You get a converging series.
It had been known that for some reason, if you heated up hydrogen gas very hot and looked at it through a spectroscope, like a prism to separate the light into wavelengths. You didn't see a continuous spectrum as you do with sunlight. You saw a series of lines. And these are the lines you see with their wavelengths in nanometers here. And they run all the way from ultraviolet through to red. And this was very puzzling. Why should hydrogen gas do this when light from the sun did not do that? And Johann Balmer, he had a PhD in mathematics, but he couldn't get a job as a mathematician in the university, so he became a school teacher, a fate which was spared to me, and he liked playing around with numerology, and he came up with this simple expression here, lambda equals km squared over m squared minus n squared, where k is some funny number here, he put n equal to 2, and he made m equal to different integers, 3, 4, 5, 6, 7, 8, 9, and by substituting into this formula, he got exactly the wavelengths which were recorded in the spectrum of hydrogen. Very puzzling. And nobody had any idea why. Why should this work? So, professional scientists took this up, and eventually Rydberg, German, generalized this into an equation here. I won't go through all this. And now, after a while, people found more series. They began to wonder, if n is equal to 2 here, what happens if n is equal to 1, 3, 5, 7, 9. So I put these numbers in, and these predicted other spectral lines in the spectrum of hydrogen, which we looked at, and there they were. And eventually they discovered this was something to do with transitions between levels. So we had all of these different spectra in the spectra of hydrogen, and nobody had any idea why. Well, along comes Niels Bohr, who, for this work, which he did in 1913, won the Nobel Prize in 1922, the 22nd Nobel Prize. And there he is as a young man. You usually see pictures of people like Bohr and Schrödinger and Heisenberg and Einstein when they're old, wrinkled farts like us and all of their good work. But all of them, in fact, did their best work before they were 30. In fact, there's a rule of thumb amongst scientists. If you're going to win a Nobel Prize, you've got to do it before you're 30, because then you're over the hill. So I'm well past it. They'll never give me one. Except maybe the Nobel Booby Prize. What did he say? He said, I have a strange theory which can predict this. He said, first of all, this is an atom. There's the hydrogen U-tube nucleus, which is one proton. You know about protons, positive, electrons, negative, and neutrons, nothing at all. It's sort of like jellyfish, green and black. But we only have, over there. We only have protons and 1 electrons in hydrogen. And he said, well, let's consider that the atom is constructed like the solar system. That there's a central sun, which is the proton, and around it goes one planet, which is the electron. And it's held there by electrostatic force, not gravity. And this is an equation for the electrostatic force. M, the mass of the electron, Z, the atomic number, and so forth. Then he made a startling prediction. He said, but we're not allowed to have any orbit, as we are in the solar system. We can only have particular values of orbits. And he didn't know why this was, but he worked out that it had something to do with standing waves. His picture over here with a hydrogen atom, and there's one standing wave. You can think of a coaxial line stretched around this with one standing wave on it. And then you can have one with 2 standing waves and one with 3 standing waves. And there are rules for calculating the wavelength. And these were the only ones that could survive. The orbit radius is quantized. So only certain orbits were allowed to exist. And then furthermore, he used an equation which had been developed by Max Planck earlier to explain black body radiation, which said if an electron jumps from one orbit to another orbit, it changes its energy, and the wavelength that's generated by that transition is given by this lambda equals CH upon EI minus EF, where C is the speed of light, H is Planck's constant, and the energy. And this was successful. It worked. And it seemed that everything was explained except for this puzzling thing, why were these other orbits not allowed? So, here's a bit more about it. Characteristic X-rays. Bohr's theory was extended by Moseley. Unfortunately, they found that although Bohr's theory explained the hydrogen atom, it didn't explain helium. In fact, it didn't explain any other atom at all. It only worked for one atom. And when they looked into it in more detail, it didn't even work really very well for atoms of hydrogen. So anyway, people by this time knew that there were two spectral lines in X-rays. Whoops, we'll go back again. Go back again, the alpha line and the beta line. I won't go through all this because we don't have any math. I'll come back to it if you've got any mathematical questions, which you don't. So what is going on here is that you have a heavy element. Just go back here. The wavelength, you need a very large Z, which is the atomic number. That's the number of protons in the nucleus for good X-ray production. So you want a heavy element and you want a lot of energy. And what happens is that you bombard this material with an electron beam, and the electrons come through and they bash some of the electrons in the atom out into outer orbits, and these electrons then decay back into the ground state, and that's what gives you the characteristic radiation. So this is a picture of this over here. The first X-ray tubes looked like this. Anode with a tungsten target. This is a very inefficient system. About 99% of the energy goes into the production of heat. So these things get extremely hot. Here you have a filament. These days it's a 6.3 volt filament, and this is angled slightly, so a beam of X-rays come off like this, and you have a high voltage supply across there, somewhere between 50 to 100 kilovolts. And this worked quite well. By the 1920s, the X-ray tube evolved, and it looked like this. Here's the cathode over that side. Electrons come along here. The anode is this thing here. It's angled at 45 degrees. The idea is the electrons would come along, bash into the anode, and the radiation produced would come out following the angle of reflection straight downwards. A modern X-ray tube looks somewhat different. In fact, it looks like this. We look at a cutaway diagram, and here's a schematic over here. Now, you may have heard, I think we probably all had an X-ray at some stage. An X-ray machine looks like this. You lie down there, or you stand up, and the first thing you hear is something inside the X-ray machine winds up. What's happening is that this is a rotating tungsten target. It's tungsten because tungsten is very good at dissipating heat, and it's rotating to dissipate the energy over the entire surface of the tungsten. And what you hear, the motor noise that you hear, is that tungsten target speeding up and beginning to spin around. And the exposure of a modern X-ray is very short. Anybody any idea? Ever asked your X-ray technician what the exposure is? Of the order of 100th of a second. About the same as a photograph. It used to be 90 minutes back in the old days when people used to burn their hands off. So we've improved a lot since then.
Is it the films that have improved?
Yes, the films have improved. It's mainly films. The first ones, they didn't have panchromatic films, they only had orthochromatic films, and they really didn't understand how to produce. The X-rays they produced were not filtered, and they had a lot of components in them which we now know are harmful. It's good, which I'll come to that later on. So that's a typical modern X-ray apparatus, which we probably all see. Has anyone here not had an X-ray? Isn't that interesting? It's something that we all take for granted now. You've probably been to an airport too and had your baggage scanned, and this is what the baggage scanner sees. They don't normally let you see this. The software inside these things is extremely clever, and it colour codes them. And you can see here there are all sorts of things inside here. There are key rings, and that looks like a money changing thing, and so forth. So if you're carrying a Derringer or a Colt 45, they can probably see it. They're also introducing these in US airports, full body X-ray scanners. Now at the top here we see a picture of a person, and in the front and back scans we see he's got a gun concealed by his bottom, and he's got another one concealed down here on his leg. And his companion, the nice looking Sheila here, she's got a gun concealed on her bottom as well. So all you have to do is pretend you've got to scratch your bottom, come up, start blasting. These are very recent. They use long wavelength or soft X-rays, about 30 gigahertz. That's actually not all that high, is it? 30 gigahertz. That's sort of radio frequencies, which is a bit above really. But because they are long wavelength they don't penetrate the body very far. They're predominantly stopped and reflected by the skin. In fact, what happens is that a very narrow pencil beam comes out and it scans the body like this. Typically you stand like that with your hands up or your hands down in front of the screen, and something goes bzzz, and a raster scan runs an X-ray beam on you, and that's reconstituted the photograph that you see. And typically the exposure is 0.009 of a millirem. I'll come to millirems in a minute, which is only a thousandth of what you get in a chest X-ray. But the problem is, in a chest X-ray, all of the energy that you get is distributed through the whole of the chest cavity. And so the average energy density is very low. Here, virtually all of the energy gets stopped in the skin, in a couple of millimeters or so, and so the energy density in the skin is very high. And recently, health concerns have been raised that even though the total exposure is not high, it's localized. And in fact, if you go on the web, you can find people writing about, well, if you come across one of these things and they insist on using it on you, don't let them do that. Make them pat you down instead, which they can do. And in fact, we've got a little video about this here, which we will now see.
I'm going to need to see you naked before you get on your flight.
Excuse me,
I need to make sure you don't have any weapons.
why can't I just go through a metal detector?
You could have a bomb that's not made of metal.
You have a chemical detection machine too. Can't I just go through it to check for bombs?
You could also have a weapon that's not made of metal.
Why would I want to put a weapon in my ass crack if I can just break a duty-free vodka bottle and light it on fire or cut someone with it?
I'm going to need to see you naked before you get on your flight.
But what about everyone else in line?
You were randomly chosen.
Why is it that I get randomly chosen every time I fly, and my husband never gets randomly chosen?
It's random.
So, I have to take my clothes off.
No, we have a machine that sees through your clothes.
How does that work?
It uses a special kind of X-rays to take pictures of your skin.
Are X-rays a form of ionizing radiation that can cause cancer?
The dose of X-ray radiation is very small.
But don't these special X-rays focus all of their energy on the skin, rather than dissipating it throughout the entire body?
Yes, but the machines are designed to use a very small amount of X-ray radiation.
Are the machines tested to make sure they're not leaking extra radiation, the way medical X-ray machines get tested?
No, but you don't have to worry, because this is brand new technology.
Doesn't that mean that it's too early to know all of the effects on living tissue?
Scientists estimate that the risk of getting cancer from the X-rays is very low, about as likely as dying in a terrorist attack.
So how is this making me safer?
9/11.
What?
9/11.
But the terrorists on 9/11 used box cutters, which would show up when I go through a metal detector.
The terrorists will try something different next time.
So why aren't you using all of this money to secure our ports or inspect air cargo?
The terrorists smuggled weapons onto planes on 9/11.
But you said they would try something different next time.
Yes, it's why we need to see you naked, to make sure you don't have a bomb hidden in your ass crack.
Has anyone ever smuggled a bomb onto a plane in their ass crack?
No, but there was a guy who sewed a bomb into his underwear.
Did that work?
No, but he lit his balls on fire.
Would a machine that sees through clothes be able to see a bomb sewn into underwear?
Probably not. But the terrorists will try something different next time, like smuggling something in their ass crack.
Wouldn't it make more sense for them to put the bomb up their ass where your machine can't see? Prisoners do it all the time.
I'm trained to deal with air travelers, not criminals.
Well, I don't want anyone but my husband or my doctor to see me naked. It would violate my religious principles.
Okay, we can give you an enhanced pat-down instead.
What's an enhanced pat-down?
We run our fingers over every inch of your body, including your breasts, your labia, and your ass crack.
You want to grope me?
No, we'll bring a woman in to do that while I watch.
Will that happen in front of all of these people?
If you'd like, we can take you into a private room and grope you there.
I don't feel very safe going somewhere alone to get groped by a stranger.
If you'd like, Your husband can come into the room and watch a stranger grope you.
Can he record it to make sure nobody abuses me?
No. If he attempts to record security procedures, he will be arrested.
Like the koala of all America.
So it goes on. That comes off YouTube, would you believe? Amazing. Now that's actually an interesting video because even though it's a cartoon, it addresses a lot of concerns that people have had about this technology. They're twofold. One is about the exposure of the X-rays on the skin, and another is about the privacy issue. People just don't feel comfortable having their intimate details examined. However, on we go. Going back a little bit, the first attempt to look inside the body was by this man, William Beaumont, who was a doctor in Canada. And he worked for the Hudson Bay Company in Mackinac, Fort Mackinac in the Michigan Peninsula. In 1822, he came across a voyageur, a French fur trapper, who had been accidentally shot in the stomach with a musket. The wound never closed up, and it formed a fistula. Anybody here got a fistula? They're not all that uncommon. Which was connected to the stomach, and so it oozed stomach juices and food periodically. And it had to be covered to stop the food oozing out. And Beaumont recognised this was a wonderful idea to see what happened inside the stomach. And so he tied little bits of various foods onto a silk string and he pushed them inside this bloke's stomach. And he did this from 1825 to 1883. And he wrote up what he found in a very interesting book. Here's a diagram of a fistula. And here's a page from his book. He also drew out the stomach juices and put various materials in them. Here, for example, he inserted rice, oysters, pork, venison, tapioca, lamb, chicken, eggs, and custard. Up till this stage, nobody had any idea at all what went on inside the stomach, because all of the stomachs they looked at were of dead people. This was the first time the stomach of a live person had been discovered. Here, for example, he says sago. He put 1 pound and 4.5 ounces of sago in stomach juice. It was boiled and it took 3 hours and 15 minutes for the sago to completely dissolve. And he made a lot of tables like this. It goes down and down, and he's venison, spinal marrow, turkey, goose, pig suckling, and he's what all this means, who knows. But it showed that the average time that the digestive process needed to dissolve the food was between 1 and about 6 hours. Very fascinating. Well, that was the first time anybody tried to look inside a human living body. The next thing we come to is magnetic resonance imaging. Now, somebody here must have had an MRI. Anybody had an MRI? Yes. This can be a bit forbidding, isn't it? Because, now, did the machine look something like this? It's a long cylindrical thing with a little hole in, and you lie down and you're slid inside the hole. And it typically takes quite a while. How long did it take in your case?
I'm not sure now.
Well, it normally takes between 15 and 40 minutes. That's quite a way. And it's there's no X-ray involved, but it does use very strong magnetic fields. 1 to 2 Tesla. That's a very strong magnetic field. And if we look at what happens, here's another video here. We'll have a look at this.
When someone suffers from an internal ailment that cannot be detected by a traditional office examination, an MRI may be necessary. When an MRI is administered, the patient lies on a retractable platform which enters the center of the machine. Upon entering the machine, the patient is scanned by one of several magnetic coils that emit a radio frequency pulse targeted at the specific region to be examined. This creates a magnetic field that runs down the center of the tube. There are billions of hydrogen atoms within the body, which rotate on a natural axis. When the magnetic current is introduced, the atoms align to it like a compass and spin on a new axis. When the magnetic force is removed, the atoms return to their natural alignment. As they relax, they emit energy and act as a small radio transmitter. Different tissues release different energy levels, and the computer recognizes their distinct pulses. The difference in energy is determined by the atom's realignment time. Dense tissue takes longer to realign than soft tissue. So when the computer receives the different energy levels, it creates an image, which shows dense areas as white and less dense areas as black. With this procedure, the MRI can show organs, tendons, ligaments, etc. It is only because of the sheer number of hydrogen atoms in the body that MRI technology is possible.
So there you go. Just radio waves. Roughly what happens is this. We can view it in a simple-minded way. We have a little radio transmitter over here which emits pulses, very quick hot pulses, and one portion at 40 to 80 megahertz. Now the body over here, the magnetic fields in it, they have a slightly different value at all points in the body. And at every frequency here, there is a resonance at some particular point in the body. So the atoms in that part of the body, the hydrogen atoms, will radiate preferentially. So if you sweep this frequency over here, then you're able to scan the complete body. And this is why it takes so long, because it's pulsed, boom, 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 boom. And the receiver over here, just a radio receiver, picks up the signals, radio signals from the body. And it's very like the situation we have here. We have a transformer down here, coupled by mutual inductance M. You apply a tone burst from a generator, and over here you have a couple secondary here, and that picks up the tone burst and can be recorded. So it's just like a radio transmission system.